Hi, everyone. So for the next half an hour, I'll be talking about data integration and some of the techniques which we developed here at Data 61 to make the process of data integration as simple as possible. So in its broadest sense, data integration is about combining data from different sources and providing the user with a unified view of this data. And the situations actually when this problem arises are plentiful. So for example, you have multiple data sets with some common entities and content, but you don't know the schema of those data sets. Or you have siloed systems or legacy systems which you need to bring together. Or, I mean, in more general sense, you need to share data across systems or schemas, and you have to handle somehow those different schemas. So here at Data 61, we face this problem quite often when dealing with some government projects which we have, and especially when we need to do some analytical work on data which comes from different governmental agencies. This is a huge issue because we basically get a huge amounts of different CSV tables, SQL dumps, JSON sometimes, and then before we can do any analysis, we actually need to bring this data together. And a common practice in enterprise to handle this data integration issue is to construct some complex ETL frameworks. And today in the morning, in the first talk, you saw actually how complex those ETL frameworks can look, and that this is really a huge headache. So our question now is, can we use machine learning to help us solve this problem? But before I actually go into a bit more detail about how exactly we use machine learning here, or how we can use it, so the data integration area, this is quite a broad area, and there are lots of different problems which exist within it. And in our team, we focus on the following problems. So the first one is schema matching and mapping. This is actually the core of data integration, and this is exactly where we try to connect data sets by establishing a global data model. Then there is a problem of entity resolution, which is actually really crucial when integrating the data. That's basically detecting entities across databases. The other one which we are looking at is privacy-preserving analytics, and and we are interested in this issue since we have projects with multiple partners, and very often those partners don't want explicitly to share their data. So, and the question here is that can we actually learn the global data model without explicitly sharing the data in this setting? And the other issue which we're looking at is about data quality. And yeah, you've heard already great talks about this issue yesterday. The last talk was especially about it, and today in the morning as well. And our main approach is actually to try to come up with techniques which would actually automate the solutions to all of these problems. And in my talk, I will focus only on one of those problems, and mainly schema matching and mapping. And I will not go too much into detail how exactly we implement the stuff and some technical details. So I will just try to share with you ideas actually how we can automate the process of finding a global data model for our very heterogeneous data sets. So let's start with relational schema matching. And I use here the word relational since we're dealing with relational schemas. So meaning that we have some CSV files, or we have some SQL data tables. And imagine that we have 5 data tables. And each of those data tables contains a column which is supposedly has some people's names in it. But in each of those data tables, the column, it's called differently. You can see that. So in one it's called username, in the other one it's called people. The other one has it like with underscore, users underscore. And then if you look at the content, so it's also the case that the formatting is quite different. And our goal is now actually to automatically connect those data sets across these relational schemas. And the problem which we face here is actually syntax versus semantics. So we can quite easily identify that those are people's names, right? but the machine gets caught on syntax. So all those formatting issues, naming differences, they cause a problem. And what we want actually to say is that all these columns talk semantically about the same concept, namely name. And that's what we call semantic type. And now the question, the way we phrase the question is, can we automatically label columns with those semantic types? And as input, we have some data sets, and we have a set of semantic types, for example, name, address, phone in this case. And the question is, can we detect all columns of the same semantic type, where column names may be different, common entries may not exist, and there might be lots of formatting issues. And for this purpose, we designed the schema matcher. So we call it schema matcher. For those of you who are familiar with machine learning, so this problem might sound very much like a multi-class classification problem. So, exactly, that's what it is. So to solve it, we need first actually to represent each column as a feature vector, which can then be supplied to a machine learning classifier. And to construct the feature vector for a column, we designed two groups of roughly two groups of features which we calculate. One group actually uses the column headers and the table name. Here we actually use some natural language processing techniques to find out how similar the column header and the table name for this particular column to the ones which we have in the training data set. And in those for the columns which are actually for which we know the semantic types. And the other set of features which we develop are content-based. So we're looking here at the exact values which are in the column. And the features which we actually use are based on character frequencies. So the amount of missing values in the column, number of repeated values, and entropy overall of the column. But with machine learning, so the crucial part is that we need training data, right? And in our case, this training data is actually is based on the columns which we have. So imagine if you have a data table which has 1 million rows but only 10 columns. So your training data, that would be just those 10 columns. So we kind of have this problem of sparse data. So you might have really like tons and lots of data, row size, but column-wise it will be quite sparse. That's the first issue here. And the other issue is actually class imbalance. So think about it, like if the user actually told you that here there are 10 data tables, and in each of those data tables the user identified, like for example, one column which is phone number and 10 columns which are people's names. So that causes then a problem when training the classifier, that we have a highly imbalanced distribution between the classes. So these are two major machine learning issues which exist when solving this schema matching problem. And one of the approaches actually which we looked at to handle the problem of class imbalance is, the standard approach is to use various class resampling strategies. But we found out that actually using cost-sensitive learning, when we introduce asymmetric costs for misclassifications, works much better in our case. So to be a bit more specific, so think about it like you have the user provided you a data table with 50 columns, right? And then the user specified the semantic types only for 10 columns. And the other 40, the user might have been just lazy to label them, or I don't know, just not really interested in those other 40 columns, so you don't know. So we treat them as the unknown class in this sense. And then we get this problem that the unknown class is highly overrepresented. And then actually we tell our classifier by introducing the so-called cost matrix that actually if the classifier puts the real name column into the unknown class, that the cost of it is much higher than, for example, misclassifying the unknown class as the name class. And in our experience, we found that actually cost-sensitive learning performs much better than class resampling strategies. But here, actually, the other issue is still not solved, the issue of having sparse data right? So, I mean, the problem, look, you have 1 million rows, but you get just one feature vector out of it because it represents just one column. And so we're actually doing something not really right here. So how can we actually harness this, this crucial point that we have actually big data? And for this purpose, we found that bagging works really well. So in this sense that we take this one column which has 1 million rows, and instead of constructing just one feature vector for it, so we use bagging to build many smaller samples by subsampling the big column, and we get a much bigger amount of feature vectors just from one column. And this approach also handles the problem of class imbalance. So in our experiments, actually, bagging performs much better than using class resampling or cost-sensitive learning. So now actually how this schema matching process actually looks like. So the point is that the schema matching is trained on examples and user feedback, and the idea is that system improves as predictions get corrected and as the system sees more data. So a bit more specific, so at the beginning the user supplies semantic types he or she is interested in. Like, for example, in this case, name, address, phone, and email, and then the user provides the data set. What the user also has to do is actually to label some of those example data sets, so say which column is which semantic type. And then the system generates predictions, and then the user might just automatically accept all the predictions or actually correct the ones, so it depends on the system configuration. And then this way we actually add more data and the whole process repeats. So where can we actually use now this schema match, the way it's designed? So first of all, we can link and connect the data and merge the different data tables on the on those semantic types which were discovered. Then we can actually provide some class-wide transforms. So instead of specifying a transformation per each column, right, we can just say, for example, that we want one formatting transformation to be applied to all phone numbers. The other thing is actually we can now relabel columns using the semantic types to some unified naming. And we can also label no header data set. So if you have a data set with no column headers, that's not a problem for the schema matcher, since we still have those features which are based on the content. But the most interesting part, at least for me, is actually that we can use now the schema match as a component for further semantic modeling. So what do I mean by semantic modeling? So first of all, semantics is a very tricky concept, and it's because it's highly subjective. So I will share with you some ideas actually what I understand by semantic modeling for the data sets. So look, we have now a data table with 5 columns: name, birthday, city, state, and workplace. And our schema matcher can tell us that the column name is about some people's name, right? And city column represents the names of the cities. But the thing actually which we can't tell from this data table, what's the connection between the person and the city? So is it the city where the person lives in? Is it the city where the person was born in? Or is it the city where the person works in? And there might be maybe some other variations. And so there are some relationships which are implied between the columns. And when we use relational schemas, they are implicit, so we can't really see them explicitly. And this is then an issue, actually, if we want to do some analysis on the data, to better understand what the data is actually about, we need actually to know about those relationships between our columns. And this is where actually we need to introduce something like graph-like structure. And we call it a semantic model. And now the idea is that our schema matcher actually, so the schema matcher tells us only how these columns get mapped into the nodes, like that this is person's name, and location that's city's name, and content that's phone number. But our schema matcher has no way to tell us what are the relationships actually between these concepts. So, and the standard approach to introduce semantics and to talk about semantics is to use an ontology. I mean, you can also think about it as a graph schema. And there are different ways actually where this ontology can come from. So it can be either built up iteratively from definitions, so from those semantic types. If you have some experts, they can build some domain-specific ontologies, or you can download the ontologies from the semantic web. There are really plentiful of them there, but it's a huge mess, so yeah, I wouldn't recommend actually using maybe semantic web, not really very practical. So let's have a closer look actually what an ontology is. So overall, this is quite a complex structure, but we're not interested like in everything that exists and can be specified in the ontology. There are three main constructs which we need there, and that's basically what we call class node, and it represents some abstract concept, for example, organization, person, place. Then data nodes, and those are properties of the classes. So like, for example, person is described by the name, age, passport number, and so on. And the last bit is actually a relationship between concepts, right? So the links between the class nodes. And now actually, how can we construct those semantic models for our data sets? So the idea now is actually as input, we have this ontology, and we have a set of known semantic models for some of the data sets. So this is now the work which the user still has to do. And then the question is, can we generate a semantic model for a new data set? And this problem actually is known, let's say, in the database theory community as RDB to RDF schema matching problem. So the point is that we are now we're mapping actually relational database to RDF, and RDF, this is a standard, well, maybe not standard, but yeah, a rather common language which is used to express ontologies. So this is, I mean, there are also RDF-based graph databases. Yeah, so if you want to look closer at this problem, so you can search for RDB to RDF schema mapping or matching. And I will not go into much detail actually how we solve this problem, but very roughly, just to give you the idea. So we use our schema matcher to map all possible semantic types for columns onto the ontology. So first we use the schema matcher to identify the semantic types for the columns, and then those identified semantic types, we map them onto the ontology, onto the class and data nodes. And then we need to find most likely semantic model. And what actually our semantic model is, in this case, is a subgraph in this ontology which covers matched semantic types. And this is a graph problem, as you understand, and in particular we phrase it as a minimum cost Steiner tree problem. So this is a very rough idea. And then we do some graph magic and we get a semantic model as an output. And yeah, so what can you do now with this semantic model? Firstly and most importantly, you will get a better understanding of your data, but then actually you can do some other cool stuff with it. So some of the ideas which actually came to our mind is that you can do better entity resolution. So the thing about now this semantic model is that you actually know what kind of entities exist in your data. So actually these class nodes, right, like person, city, phone, those are your entities. And then you also know by which properties those entities are described. So you can actually design your entity resolution algorithms for those exact class nodes using their properties. So the other thing is that you can actually integrate now your relational data into a graph database, or you can also have much more sophisticated and more accurate merging of your data sets. And the last thing is you can do more powerful search. And let's have a closer look actually what kind of search I mean here. So the bit which I didn't mention to you about the ontologies is that you can actually have additional, so you can specify some particular relationships between the class nodes, which actually allow you to build the hierarchies of the classes. So this is the so-called subclass property. And the point here is that if you have a hierarchy then of classes like that, city is a subclass of state and state is a subclass of country, and then you do the search for some information within the country class, so actually the search can be then proceeded to the subclasses. And this is yeah, this is one particular thing which actually the ontologies and the semantic models can help you with. But then you can also introduce some additional constraints in your ontology. Like, for example, you could say that a person should have just one birth date. I mean, makes sense, right? And in this way, you can actually check for data consistency. So, yeah, you can check actually whether your data is consistent with regard to those constraints. And as for the graph database, so yeah, now the ontology can act as the intermediary between graph database and relational databases. So it's not really necessary that you have actually to upload your data to some graph database, but you can do now, by having this ontology, you can now do graph analytics. And yeah, so it functions as a graph schema and global schema of your integrated data sets. Yeah, so now let's just shortly summarize what we've talked about so far. Yeah, so I started with the relational schema matching, and I presented you how we can use the schema matcher actually to put together relational schemas and find semantically similar columns across data sets. And then I went on and talked about how we can use the schema matcher actually to find now graph-like schemas for your data. So the semantic modeling allows us not only to find semantically similar columns, but it also allows us to find relationships between those columns. And yeah, so there are really lots of issues still which are open. And if we talk about schema matching, so there are several open questions which are especially interesting for our team. So the first one is actually about transformations and complex column matches. Like, imagine you have a data table which has a column full name, and another table has the column's first name and second name, right? So you need to do a transformation, or you have actually to match this. It's a 1-to-2 match, right? So, and the question here is actually, can we do that also in an automatic way? Can we use actually machine learning to help us find such matches and such transformations? And the other two questions are about applications of semantic models in entity resolution and in search. So we're still looking at some cool ideas actually how we can use semantic models to improve and to make entity resolution and search more efficient. So yeah, that's it for my talk. Thank you for your attention, and you're welcome with your questions.